Hi there, it's Ron Gula with another episode of the Gula Tech Cyber Fiction Show. Today, we are going to be speaking with the CEO of one of our portfolio companies, Wave Engine Corporation, Daanish Maqbool. Daanish, did I get your name right?
Yeah, Daanish.
I'm always afraid of getting somebody's names wrong when it's not.
It's all good.
Let's just call it like an American name, right? You weren't born in St. Louis, right? Where are you from?
Right. So I'm from Pakistan, and I was born and raised there. I've lived, most of my childhood in a city called Rawalpindi, it's a pretty large city. It's a few million people. It's not small by any means, but it's not very well known, and it's overshadowed by like its twin city neighbor, which is Islamabad, which is the capital. And it's pretty happening childhood, pretty happening place, and basically around college time, I was like, time to apply to colleges, and in school, I was pretty inclined towards like physics, math, stuff like that. I wouldn't say I was a bookworm, but I was definitely like kind of inclined towards that. And when it came time to apply to colleges, I was like, let's apply all over the place, and by all over the place, I mean all over the world. And I was like, we'll see what happens, just to see what happens kind of attitude. And when it came to applying to the US, I was like, man, if I'm going to go that far, it better be for like MIT or something. And so I applied to MIT, and I got in and came over, sitting right here.
Excellent. So you also got a PhD in aerospace engineering from the University of Maryland.
That's right. Yeah.
So did you went to MIT first and then Maryland second?
Yeah. So I went to MIT for my undergrad and undergrad in aerospace engineering, and then after that, I came to the University of Maryland for grad school, and did my got a doctorate in aerospace engineering over there, and I've been in here in the DC area since then.
Excellent. Well, so you're the CEO of Wave Engine Corporation, and when I first met you, we met at the Maryland Momentum Fund, right? So that was made up of cyber investors and doctors, and a lot of times the healthcare people would come in, and I'd be all impressed, and they'd leave, and the doctors would be like, foo, maybe not, And then some cyber guy would come in and try to sell us better password management, and all the doctors would be excited to be like, hey, that's good, but that's kind of been done. But a jet engine company comes in one day, and since there were no jet engine people there, we all invested, which was kind of good. So what is North American? Actually, and that gets back to the thing here. When we first met, it was North American Wave Engine Corporation. Now you're just kind of going with Wave.
Yeah, that's
Engine.
right. So the company's actual name is North American Wave Engine Corporation, but it's like, I thought it was really cool, and everybody really liked the name, but then there was like a change of heart, and everybody was like, it's really long. The acronym is really long. People get confused.
NAWEC sounds like a division of the military.
Exactly. Yeah. I got that feedback a lot. People were like, it sounds like, some division of the Navy in particular, and especially the way the logo was. A lot of people would get confused. They'd be like, is this a private company, or is this like, some Navy center or something? And so we were like, we need to go with something a little more, something a little cooler. So we just went with Wave Engine.
That's awesome. And that's a good lesson for a lot of the entrepreneurs out there. It's like, they get really attached maybe to the first idea they have, and maybe it's a great idea, and maybe that they get so attached to it, it kind of becomes a hindrance. That's kind of cool. I think Wave Engine sounds kind of like Tesla. It sounds cool.
Yeah, it's cool. It's like, it's something that, I think some people just, call it Wave. It's more familiar than, like NAWEC, for example. So yeah, I mean, it's not like familiar in the sense that it's a new technology, right? We're trying to make it like it's a new word, so to speak, but at the same time, it's not like a weird name. It's not something that you look at and you're like, how do I pronounce that? So I think it sounds just right.
Cool. So what is unique about the engine?
Right. So the engine, so it's a jet engine. It's got no moving parts. That's basically the main differentiator, or the new thing about this engine. And typical jet engine out there today, very complex device. Commercial aircraft engine can have over 70,000 moving parts. So it's something that, it's among the most complicated, and expensive machines out there in the world today. But, if you can take that and turn it into something that has no moving parts, I mean, it's obviously a big game changer for aviation.
So when people think of no moving parts these days, they think of electric cars, right? So this is not an electrical engine. How does this work?
Right. Yeah. So this isn't electric. The thing about aviation is that I know there's a lot of talk about electrification of aviation, but if you want to get to the kinds of speeds that commercial airliners or military aircraft are getting to, and the kinds of ranges that they get to, the amount of energy that you would need is just way too much for traditional batteries to be able to provide. I mean, to run a car is one thing, but to fly an airplane is like it's an order of magnitude difference. So no, it is an engine in the sense that it converts fuel or thermal energy, and it uses it to produce thrust. And that also kind of speaks to one of my pet peeves, is that engines are devices that convert thermal power or heat into mechanical power or mechanical energy. And these days, people just use engine for like everything. It's like, as an engine guy, somebody who's studied engines from the beginning to the end. It's like, that's specifically what an engine is. But these days it's like people talk about electric engines and stuff like that. But yeah, no, this is a conventional engine.
Gas goes in, yep. Hot air thrust comes out. Right.
Exactly. Yeah.
So it's been really interesting to know you on this journey so far. When the first few times we met, it was all about getting the prototype up to a certain level. Then it was like test flying it. So do you mind if I show the video when I stop by?
Absolutely.
And so I got a video here, and let me just maximize this here. And why don't you tell me what's going on?
Sure. So that over there is Nitai, and he's one of our engineers. And Nitai does an awesome job of building the electronics that control the engine. What he just did over there was he hit the green button, which started the engine. And so this is kind of like your car. It's a digital control panel. You just hit a button, engine started. And he hit the red button now. I don't know if you saw that, and that turned the engine off. And that's actually, I want to point out, this is something that's very unique when it comes to jet engines in particular, because to start a jet engine, you need, generally speaking, a turbine engine. You need a lot of air. Okay, so it's a whole startup procedure. You can't just turn one on. It requires like a lot of spooling up time and all that. And so the fact that you can turn it on and off so easily, with like minimal amounts of air, is something that is very interesting. It's very we didn't really, initially when we first made this thing, we didn't think it was a big deal. But then after that, when we spoke with some of the companies, right, and some of the ultimate users, they were like, "Whoa, how did you turn that on?" We're like, we hit the button, and it just hits it with a shot of air and it turns off. They're like, "Really, you can do that?" We're like, "Yeah," and we're like, "Is that a big deal?" They're like, "Yes." And we're like, "Okay." So then we learned from the potential users that was kind of a big deal, because starting these engines is a huge pain, and so especially if you don't have ground infrastructure. So the thing is, like, if you're on the ground and you have like a whole bunch of infrastructure around you, you can go ahead and start it, right? But so you're in the air, okay, it's actually very difficult to get all that air to start these engines. So that is an interesting attribute what you just saw over there.
So you can start from no moving air; it just works.
Yeah.
And I'm not going to pull it up again, but it looks like it's a U-shaped.
Yeah.
So how do you get thrust if you're both pointing? One. I'm assuming like of a single rocket. It's not a rocket, right? So you're exploding gas. And how do you get propulsion out of that then?
Yeah. So basically what happens is this pipe, I mean, think of it as, so let's just start off with visualizing this as a straight tube. What you would have is, say you had like an open-ended tube, like a, not a flute, but just say an organ pipe or something like that, right? You would have a resonance inside this tube. Okay. So basically like it would want to resonate at a certain frequency. And what that resonance would imply is that it sucks in air from both ends and it lets out air at both ends. So it's kind of like breathing. The tube is breathing, That's what musical instruments do. This is essentially the same thing, except that in this case, the resonance or the breathing energy is provided by gasoline. So basically, you're using combustion to drive essentially a musical instrument, and so you get air flowing out both ends, and you get air coming in from both ends, and you can use that to produce thrust. And let me try explaining this a little differently, Ron. So if you have the engine works essentially like this, you have a U-shaped tube. And you set off, a combustion event inside the combustion chamber, somewhere inside the tube. Now, what that does is that, you get these combustion gases that are very hot, very high temperature and pressure, and you get these jets of hot air going out the back. They go out both ends. And what that does is now, ordinarily you would think, okay, so you had an overpressure, now the air's gone out, it's going to come back to like atmospheric equilibrium, and that should be the end of it. But air has an interesting property in the sense that it tends to overexpand. So it has like, it has a spring-like nature, which is also why we can talk, the reason why sound waves exist. And when that overexpansion happens, you end up with a vacuum inside the tube. And that vacuum tends to suck in fresh air after the first combustion event. And so you get this sequence in which you have like a combustion event, you get a hot jet of gas going out, then you have a vacuum inside the tube, it sucks in fresh air, and then you can inject fuel and burn that gas again, and the cycle repeats. And you can do that at about, in our case, we do that about 100 times a second. And so you get these intermittent, jets of air going out, and you can produce thrust. And it's very much like a squid, actually. The way a squid, like, tends to open up and then it like shuts it, shuts its like whatever those are, and, you end up with like a vortex, like a slug of, fluid going out, very much like that, except it's gasoline powered and it's, driven by sound waves.
Now it's a single part. I mean, I guess technically you could get in there and take that spark plug out, right? That's igniting things, but there's no moving parts, right? I mean, that's just insane. Yeah. Is there any better advantage in like gasoline used per velocity than a regular jet engine?
Yeah. So can you elaborate on that a little bit?
Okay. So if I was going to put this engine,
right.
So this engine, first of all, we in jet engine, you speak of thrust power, right? So how much thrust are you making with this?
Right. So, that's actually another really important differentiator here. So, typical jet engine, turbine engines, you can make engines that are really small, like 50 pounds of thrust, 20 pounds of thrust. But they're mostly used for, things that produce thousands of pounds of thrust, so like, an F-16 engine is going to be like, 20,000 pounds.
Yep,
exactly. Yep. And, the, airliner engines, also like going up to like 100,000 pounds of thrust or so. So, I mean, those are big, that's a lot of thrust. These kinds of engines are more suited for smaller amounts of thrust. So, naturally, the sizes in which they would tend to work well, and the sizes that they've been studied at and that we built them at, is somewhere under 1,000 pounds of thrust. And that's kind of interesting because the way that the industry is evolving is like, with aircraft tending to get smaller, that actually fits in pretty nicely with the thrust range that smaller aircraft require. And it's also interesting because, I like to point out to people that the reason why you have airliners, that constitute most of commercial air travel is basically because of this size constraint or size regime of the jet engine, of the turbine jet engine, right? So let me explain that a little more. So traditional jet engines, like turbine engines, they tend to operate well, or they tend to be efficient when they are large. So when they're producing like a few thousand pounds of thrust or beyond. When you try to scale them down in size, they tend to become very inefficient. Their lifetimes end up being like very poor. The technology just doesn't scale well when you bring it down. So essentially, the only way to make an efficient and reliable jet engine is to make it big. And that means the airplane has to be very big. And so that means you have a problem, a technical problem and an economic problem if you try to make engines small to put on, small aircraft. Like, for example, if you tried to put a jet engine on a Cessna today, the cost of that jet engine would be about the same as the cost of the airplane or more. So, like one of the smallest turbine engines you can buy today, it's something like a Pratt & Whitney PT6. I don't know, what does it cost? Like something in the vicinity of like $700K to $1 million. A small aircraft, so like a small Cessna or something like that, would cost somewhere about $500,000. So what I'm trying to say over here is that that's
math, like more expensive than the jet.
Yeah, exactly. I mean, the math just doesn't work out, And so the thing is, like, this is a problem that a bunch of it's a problem for a bunch of applications in a bunch of sectors, And so that so the fact you brought up the size thing, and it's interesting because this technology is kind of more suited towards the smaller end of the thrust spectrum, and so it can start to fill in those gaps, for smaller aircraft. And that's what makes it very interesting.
Well, when I see these big drones that have 12 rotors on them this is what you're talking about, right? You're talking about these large drones that could be used for delivery, for military purposes, for reconnaissance, for attack. We'll get into this here in a minute. But so have you tested this? Have you flown it?
Yeah. So
I'm doing a bad job pretending I don't know these answers. Of course you have, right?
Yeah.
Right. I got video queued up.
Yeah. I mean, yeah. So basically, so we've, in the evolution of this technology has been like very, in general with technologies like this, it's kind of slow, just because everything just takes a lot of effort to develop and a lot of like money, and there's a lot of like regulatory stuff to deal with as well. So it's just like it's a slower process than most people are accustomed to, I would say. And we started off with just very basic lab scale engines running it at the University of Maryland. And then we transitioned off with more funding support onto larger engines. So engines that are now running on gasoline, putting out real world thrust levels, things that could actually push a plane. And we ground tested those. And then after ground testing those quite a bit, we eventually put it on a small plane. We start flying around. And so, yes, we have tested it.
All right, this is right off your website. So let's take a look at this. And first of all, I just want to say that when I first met you, it's your first company. And we were talking about getting logos, getting your marketing down right. This is an amazing video. So how did you? First of all, congratulations on a successful test flight, right? That's awesome, right? But a lot of times when people have something like that, they don't put it front and center, like on their homepage. So this is really cool. So what's going on here?
Yeah, so that is it's basically footage of our test flight. Of our second test campaign. And what's going on over there is that you have the engine that we mounted on a small aircraft, the Shredder H-14 glider. And we wanted to use that as a proof of concept, of the engine pushing an actual plane. And it's not a UAV, like a lot of people assume it's a drone, but it's actually a manned aircraft. It's got a person inside it, pilot's name is Sean. He's awesome. I'm a big fan of him. And it was just really cool. I mean, to see that, our plane pushing an airplane, actually flying that airplane. And, another thing I'd just like to point out that, everybody sees the engine on top, but like all the real effort, I would say like 80% of the effort is inside the airplane that you can't see. So all the fuel system, all the controls, all the electronics, the control tower had to be like completely rebuilt to have like, the engine controls put in. There's just a lot of work that's gone into that plane, and you just see the thing at the top, which is kind of like the thing everybody's looking out for. But yeah, that's the first aircraft that the engine went on. It was a really good proof of concept. We were very happy with what it did, and now we're looking forward to kind of taking it farther, expanding the envelope.
Now you say it's coming soon. But what is it? So it's you're working with customers now, right? You've got a lot of different folks. So who's working with you? What are people using this for?
Right. Yeah. So in the grand scheme of things, I think the pathway that is going to be followed, and this is fairly typical for technologies like this, is that the first people willing to take on a development effort like this and take on the technical risk for something like this is usually the government. So we have a bunch of, government programs that, we're into. The first one was with DARPA. Okay. So you want me to get into that now, Ron? Or
Well, you should mention what DARPA is probably.
Sure. Yeah. So DARPA is the Defense Advanced Research Projects Agency. It's the arm of the Department of Defense that's been tasked with, high-tech R&D, developing new technologies, that could have an impact for the DoD and beyond. And so DARPA generally, in case somebody doesn't know about DARPA, I'm sure, Ron, you could probably give a better intro to DARPA than I could. But, DARPA has had a hand in developing almost everything, cool technologically you could think of, everything from, the internet to, stealth technology to, I've heard even mRNA vaccines, So, I mean, everything kind of starts off with some kind of DARPA funding, DARPA getting their, DARPA, getting promising very early stage technologies, some traction. So our first, kind of interaction is basically with DARPA. First contract was with DARPA to, scale this thing up, expand the flight envelope and, just get this thing onto a onto a platform that can do more than what we have right now. And then beyond that, we also have a contract with the Air Force that is to develop a decoy. And we call that the VALP, the Versatile Air Launch Platform, the VALP. I think the acronym sounds really cool, actually. So now, after having done these, after having gotten this proof of concept, basically, the next stage is to get this onto platforms. By platforms, I mean aircraft that are actually doing, real world kind of. Real world kind of mission profiles, And
I've got a screenshot up of this. I think this is the artist rendition of the VALP. What does VALP stand for?
Right. Yeah. So it's Versatile Air Launch Platform. And the whole idea is that this is something that's fired off of or launched off another aircraft. So over there, you have a fighter aircraft and it carries that and it can launch that thing and it acts as a decoy, basically. And that's basically, one of the first applications that we have for this.
It looks like a mountain in the Chinese range, maybe. I don't know. We'll see what's going on here. So, if you're going to do a decoy, this thing doesn't look like it's going to fly back and like dock with the F-16 again, right? This is a fire and forget. This is cheap. This is a decoy. This is saving human lives. This is cool, right?
Yeah, this is one of the reasons why this is an attractive technology for an application like a decoy is exactly what you said. It's cheap. It's perfect for disposable applications. For like a decoy. You fire that thing and it's done. Putting a jet engine into a turbine engine into a decoy is something.
It's expensive.
Yeah, it's expensive. And so for applications like this, it makes perfect sense. And let me know when you want me to talk about the.
Oh, you can talk about whatever you want to talk here.
Okay, cool. Yeah, no, I was just gonna kind of draw the arc basically to go from the government funded applications to bridge to the commercial world. And what we think is going to be the future for this. So basically, yeah, I mean, like in the arc of technologies like this, when it comes, even if you look at the turbine engine, anything, pick up pretty much anything like this. You'll see that the first applications are government funded because the government is the one willing to take on the technical risk, and the government has the the understanding and the resources to kind of field something like this and develop it. And then once it's matured, it can then be transitioned off to the commercial space. When it starts becoming clearer what the thing is, and for the commercial space, it's interesting because we think that there's a lot of potential there, probably even more than the government. And the reason why I say that is because, there are a couple of reasons. One is that, commercial drones, like delivery drones, not just delivery drones, but let's just say commercial drones. Okay. They're pretty handicapped right now. Almost all of them use electric motors and batteries. And that means that the ranges that are involved and the speeds that are involved are very limited. Sure, there are some engines out there, but they also have some pretty serious handicaps. Like, for example, like a typical piston engine, can't get you to very high speed. Okay, so it's not very attractive. I mean, if you have a piston engine that's doing 50, 60 knots, are you really more efficient than surface transportation? No, you're not. You're basically so there's some problems over there when it comes to turbine engines. Also for smaller aircraft like commercial drones, you're going to have issues with there's major issues with reliability. I mean, some of these engines have lifetimes of say 25 hours. Okay, I mean that's really not good. I mean, what that basically means,
that's not good for delivering me the latest book I want to buy.
Yeah,
right.
I mean, it's like it comes back to the same thing you mentioned earlier. It's like it's essentially a disposable engine, you see, and the economics just don't justify using something like that. So if you can have now a power plant that is it can give you high performance, right? So it can give you those jet speeds, but at the same time it's economical, right? So it's simple. Okay, that I think is the that I think is very attractive for the commercial world.
I've heard you talk about this before, and I'm imagining, I wish I had it queued up, but like the scene from Star Wars and Coruscant when they're looking out the window and there's almost this highway in the sky one transport going after another. And I don't think it's going to be these little tiny drones dropping off little things at our house, right? It's going to be it's going to replace trains. It's going to replace the infrastructure of how stuff gets moved around the country.
Yeah, I mean, definitely. And the thing is, again, it's not just goods, it's also people. So the thing is, it's one of the things I talked about earlier, is that the modern air transportation system, I mean, what is the reason that, we go over to BWI or Dulles, and stand in line for an hour and, just like, it's a nightmare. It's because everybody's got to pack themselves into this can, okay, with like a couple of hundred other people and go down this massive runway. The other option is you could, like, the average person could basically just, instead of buying a ticket to go on a large plane, there's about 5,000 small airports in the US. And there's about 1,000 in Canada, and that's a lot of airports. And, there's basically an airport within 15 to 20 minutes of wherever you are, pretty much. And the reason why you can't really use those is because they're small, and you've only got small planes there. And those planes are not going to get you very far, and they're not going to get you there very fast either. And the reason why they can't do that is because of the power plant. Okay, they're all mostly piston-driven aircraft. Most personal aircraft are, piston-driven aircraft. There are very few jets that, people would personally own. And the reason for that is that the jet engine is very expensive. Like we just talked about, the economics just don't work out. What if you could change that? What if you could have an engine now that took you very fast? Okay, I mean at jet speeds, but it was very cheap and very simple. That I think could also have an impact on, just transportation of people as well. So it's not just goods, it's also people. I think if we change the power plant, we can warp some of the air transport infrastructure, and that's ultimately what we want to do.
So we heard a little bit of it before when we played it in there, but this is a loud engine.
Yeah.
So how do you, if you're going to do this in the commercial, I don't like it when the BWI jets fly over the house here. So how are you going to handle the sound?
No, that's a great question. So when people, look up this technology or read about it or dig a little deeper, one of the first things that they'll come across is, noise is an interesting challenge. I mean, noise is one of the primary challenges with this. And let me just comment a little bit on why noise is a challenge fundamentally. So, in a regular jet engine, so noise is vibration. Okay. Noise is, it's an unsteady phenomenon. Okay. In a regular jet engine, you have a steady stream of gas. Okay. And any noise that comes out is a byproduct. It's like a secondary source of energy. It's wasted energy. So the perfect jet engine, the turbine and jet engine, would have a steady stream of air. Okay, there would be no vibrations and there would be no noise. So, a very, very, very small fraction of, energy gets leaked out into vibrations, and that causes a tremendous amount of noise. I mean, like a fighter engine, you've probably seen like an F-16 or an F-22 fly by at an air show. Those things are, the ground shakes. It's incredible, and the amount of energy that is actually being transmitted into sound is, I don't know the exact number, but it's somewhere on the order of like 1,000th to 1,000,000th of the energy that's actually in the plane. So, I mean, just gives you an idea of the amount of power that thing's got. So, but this engine, because it breathes, it's intermittent. That means that fundamentally, even the perfect engine would have noise because the thing is fundamentally unsteady. It's going to be creating pressure waves, and that's a challenge now. That even if you were to create the perfect engine, it's going to create noise. So fundamentally, that's why it's loud. It has this reputation for being loud, and but things have changed. There's been some interesting advancements. I would say over the past few years that allow us to really address that. So there are two things. One is, two types of solutions. One is technical and the second is operational. I'll talk about the technical aspects of this first. One of the things that we've been able to do and we were able to show at the University of Maryland was it's possible to take two of these engines and run them in anti-phase. And what I mean by that is that we can take two of these engines, marry them together, and we can have them operate so that when one is firing, the other one's ingesting. So they're firing alternately. And what that does is it can get those pressure pulses to cancel out each other, and that really drops the noise and vibration level.
Sort of like Bose noise cancellation headphones, right?
Exactly.
Bose.
Yeah. No, exactly. And it's definitely very similar to that. And the thing is, there's some more, there's some, before you can do that, there's some preconditioning steps you have to take to like clean the signal and stuff like that. But fundamentally, like, yes, you can get these things to fire in anti-phase, and that has an effect on noise and vibration. So that's one development. I would say that there's like a, that there's a technical, aspect of doing this. But the second one is operational. But what I mean by that is, over the last few years, electric aviation has actually made a lot of progress. I know I just talked about that, how the batteries are limited and you're not going to get very far and all that, right? But this is where it starts to get interesting, because electric aviation, as far as electric motors and batteries are concerned, they're very good at getting aircraft off the ground. Okay, so if you want to simply take off an airplane, get it.
Well, the acceleration of a Tesla in these electrical cars is just amazing, right? So you shoot down the runway, get airborne.
Yep, exactly. It's perfect for that. And so the idea is that if you can basically shoot down the runway, take off, get up to a few thousand feet, and then turn the engines on, for cruising. Okay, so that way the engine doesn't turn on, unless you're like a few thousand feet in the air, at which point you don't hear it on the ground anyway, because all the noise is basically all the noise regulations and all the perceived noise is basically when you're on or around the ground. So that's it opens up a very interesting space for us. And it also addresses the shortcomings of the electric powertrain as well, because the thing is, you only now need, in that kind of architecture, you would only need the electric drivetrain or powertrain for takeoff and for landing. You can
which is where you're in the most population vicinities and everything.
Exactly.
That's a great idea. That could definitely revolutionize, like you said, travel to these regional airports. Pushing supplies around. Yeah. Which is interesting. And
Ron,
then
I want to add that, like the thing is, the key over here is that you don't need a large battery pack, because you're not using the electric power for cruising. You're only using it momentarily, like you're only using it in short bursts on takeoff and for landing. And when you're cruising, you get to cruise at high speed. Okay. But the most important thing about this is this, Ron, that this kind of architecture can scale down. I mean, the other propulsion architectures or engines, right? Scaling them down is a challenge. The thing with this is both the components of this, the engines and the electric powertrain, those are scalable down to small sizes. And I think that is very key. The scalability is key over here.
Yeah, once you have that different sizes, industry and demand's going to figure out, what routes are the best.
Yeah, exactly.
Which is why we have these trains that are like, 5 miles long, or, airplanes that are the size of 747s, right? Yep. It's the economics dictated, but now we can actually have, demand dictate that.
Exactly.
So when you think about sort of the future of aviation, we can talk about the future of warfare, future of that. When I imagine that sled, if you will, being launched from that F-16, right now it's a decoy, but that thing could have missiles on it in the future and take the fight further, into the air with command and control. And you could even have cyber weapons on stuff like that. So what do you see as like the future, like drone and unmanned, air combat?
Yeah, I mean, so, fundamentally, with an engine, you can do a lot of different things, like you just said. So once you get the propulsion technology and the general architecture of the aircraft that are going to utilize this figured out, the sky's the limit. It's a clean sheet of paper. There's a lot you can do. And that's kind of the objective with a lot of these government programs, is to not just advance the propulsion technology, but also figure out what the aircraft are going to look like. So right now, for example, what do propeller-driven aircraft need to look like to perform well? The answer is pretty well known. What do jet aircraft look like? The answer is pretty well known. For commercial transport, you can see they all look the same because the designs, everybody's figured it out. There's an optimum for the design. We know what works well. What works well for fighter aircraft? They don't all look the same, but it's pretty well established what the design principles are.
MiG-29 looks like an F-18. Yeah.
It's all, with this kind of engine, this has not been actually, no one really knows the answer to this right now 100%. So that's part of what we're doing. And the important thing over here is that, we have a good team to help us figure this out. And that's why in a lot of these government programs, it's like we are taking part, basically we're specialists on the engine side, but then we have some very good partners on the the aircraft design side. So to help us figure that part of the equation out. So I would say that is also equally important. But once that gets figured out, right, I think it really opens up the aperture for a whole host of different applications, like you said. The sky's the limit.
I had the chance to visit a drone company called Platform Aerospace, and their big thing was that they could have a drone go on site for like weeks. Well, days plus, week plus few days, right? Yeah. With vanilla, which is really amazing. And they were like, we can carry this 100-pound payload for this long a time. And the one thing I learned was that most people who do drone operations are just, when they've got, something flying in on a target, they've got one flying in, they've got one flying out, they got one on station. This is like a whole drone operation thing, right? So when you have something this transformative, like what's some of the feedback you've been getting from the customer? Like, oh, this is not possible. Like what kind of naysayer stuff are you hearing?
Well, I mean, there's definitely,
of course, they're wrong, right?
There's definitely been some, I would say a lot of these, I want to use the word annoying questions, okay? But
you're a professor. No questions are annoying, right?
So the thing is, we got a lot more of these questions, I would say, a few years ago, and especially when it came down to technical and operational, aspects, and a lot of times I would be like, it's like, there's a lot of unknowns. I get it. I don't have the answer to every single thing. Okay. And at some point you just have to acknowledge that, we're going to have to do it to find out. Okay. There's a certain amount of risk that you have to accept. There's this saying, I just love it. There can be no progress without risk. Okay. And, over the years, I think we've answered most of those things. And the thing is, now we're in a position where, more and more of those things are being answered every day. And now I'm kind of, so the first demonstrator you just saw, the video we played up, I'm hopeful. I expect that, the next set of demonstrator, videos and those things will come up soon, in the next, year or so. And when that happens, it'll answer even more questions, so I would say we've definitely gotten a lot of, there's like a million questions around a million things, but, over time, those things have been answered, or just been shown to be not issues. But it's just a process you have to follow. And in this case, it's an especially slow and frustrating process, I would say, because, everything just takes so long,
One of the things I wanted to talk about was this concept of vertical takeoff aircraft. So I've got a F-35B video here queued up, and this version of the F-35's got the vertical takeoff. And so what's going on here, and what are some problems with normal, turbofan, jet engines?
Yeah, I mean, so this is now, not specific to the F-35, but just in general, when you try to use a turbofan for vertical lift. One is obviously that it's very expensive. It's a complicated machine, so, you could use it for something like the F-35, which is a very expensive and complicated aircraft, but, when you try to put it on some kind of a mass market or, try to commercialize it in kind of like a, mass market sense, it really doesn't, it's kind of hard to justify economically. And then you run into other issues, like, for example, there's some technical issues as well. So operating over unprepared surfaces. Okay. You're going to have a lot of those problems, when you start, if you try to put this thing on small aircraft that, are being used commercially on a very, very wide scale, and they're trying to land everywhere and trying to do something like that. Not only are they expensive, they're going to start sucking up a lot of dirt. They're going to start setting your lawn on fire, stuff like that. So there's definitely operational challenges over there too. I mean, a lot of these, I'm sure the F-35 has done this, but I believe the V-22 has also been done. This has been, damaging carrier decks and whatnot, So a lot of these technologies, are not practical for civil use. They're not practical for commercial or for civil use. Yeah.
What about the stealth characteristics of the engine? Is that something that's also a positive?
So that is an interesting point because that's something that hasn't been explored in detail yet. Now, there are definitely some ideas, there are definitely some possibilities over here. in the sense that you could probably make it out of a non-metal or something like that.
Yeah, I always felt, I don't think this is classified or whatnot, but I always felt like you could paint a target with a radar and get the rotor count, and you can use that to kind of fingerprint, is that what kind of aircraft that is? And this is obviously something completely different. So,
yeah.
So as you think about the future, I kind of like to look to science fiction, for that. But something I kind of told you I wanted to take a look at when you see some of these like UFO videos that are out there and some of that Navy stuff, people zipping into action like this. I actually say I know a guy who can make engines who, if this thing could hover, it could go. Now, I don't think you can go Mach 2, 3 with this engine, but you can simply turn this stuff on and get going. So when you see stuff like this, does this scream like alien technology, or does this scream like maybe something made here on Earth?
I've looked at this. I am super fascinated by stuff like this. I've actually looked a fair bit into these videos and all that. And this is just some really wild stuff. I mean, honestly, like, some of the stuff that's being described is truly out of this world.
If it wasn't for the lack of sound, I'd be like, I think you've got a night job with not DARPA, but maybe the CIA or the NRO or.
Yeah, no, it's like, with what's this. I mean, honestly, like, there is just the kind of speeds that are involved, Ron. I mean, it's like it's a different world. And here's the real thing. When I first saw this stuff, right, I was like, how do you know it's not some kind of, if it's all optical, right? You'd be like, there's something else going on, whatever. But it's been in the news that this is not all just optical. They picked it up on radar. They picked it up on, thermal image. There's thermal imagery of this stuff. There's a lot of stuff like that, and it is very, very intriguing as to what this is. There's all kinds of theories about, could it be, some other man-made stuff? I don't know. I mean, if you've got the capability to, pull off stuff like that, there's no reason for you to be doing building aircraft carriers and fighter jets, if you can pull that off. So this is really interesting. I don't know what it is, but boy, it has really, really, confounded me. I'm very intrigued. I started watching the X-Files because of that.
That's dated now, right? We've got newer things to watch. I was going to bring in a UFO model that I love talking about UFOs and that kind of stuff. But I was imagining if you took like 4 or 5 of your engines, you pointed one down, you pointed one a couple different ways, you could put that. I mean, that engine itself was like 5 feet long. So if you want to make something like that, I can remember sitting there trying to calculate from like a electromagnetic wave, can you build enough electrical force to fly through but I was like, I thought that was kind of neat.
Yeah.
So we'll see if one of them crashes in one of your engines, and then we'll know what you're doing. But so let's look at some of the examples in Hollywood and just talk about thrust to weight and stuff like that. So Absolutely. I've got the Dark Knight Rises queued up here. And of course, Bruce Wayne has the iconic scene where he takes the nuclear reactor that's going to blow up Gotham City. And he flies out on the Batwing or whatever this thing is. And it kind of looks like there's a turbofan in there. You got some stuff going on there. I'm not too sure how heavy that thing is he's carrying. But, that could have been an Apache helicopter with a rotor wider than the entire thing. When you think about your engines and jet engines, is something like that even possible?
I mean, so with our engines in particular, that, it all comes down to, Ron, what you just said, the weight. Okay. Don't know how much this thing weighs. Now, is it possible to lift something vertically like that and get like a little craft like that going? I think it is possible. But, what it's going to lift and how far it's going to go. Those are the two things that, really dictate everything. And this is the thing actually there's a lot of weird vehicles you can make. But what they'll do, what they're capable of is really what matters.
I think one of the first times we chatted, you talked about maybe a C-130 size ship, airplane that would come in and the wings could tip up with your type of engines and you could land vertically like that vertical takeoff.
Yeah.
But you'd have like maybe 4 or 5 on each wing.
Yeah. I mean, well, the interesting thing is that Boeing actually was interested back in the mid 2000s. You can look this up, but they were interested in taking a whole bunch of engines like this, and putting them into the fuselage of an aircraft, something the size of a C-130, and getting that thing to take off vertically. And so a concept like that is on paper, it's possible on paper, and it's one of those things that, I believe that some of the practical challenges that were run into before, which was basically like, well, if you have a lot of these engines firing, it's like it's going to lead to uncontrollable noise and vibration, and that's a valid thing to be concerned about. It's like those things with the understanding we have now, those traditional challenges can be addressed. So I would say that it's always been a technical possibility. It is now closer to being a practical possibility. Yeah.
Excellent. So we were talking before, you're not really a Marvel fan.
So, yeah.
So this is a scene from Avengers. They're on basically a aircraft carrier, and they're flying it with 4 giant rotary turbofans.
Yep.
I mean, as an aerophysicist, PhD, when you see something like that, clearly this is Hollywood, right? But are you doing like what is totally wrong about this?
You know what? So here's the thing. Just looking at it, okay, I can't put my finger on exactly what's wrong about it. Now, let me just say this. Generally speaking, you want to look at, whenever you're talking about seeing rotors lift something, it's all about the size of the rotor relative to, what it's lifting. If the rotor's too small, you're like, there's no way a rotor that's going to work, In this case, it's like just completely eyeballing this. Okay, it looks like the rotor might be okay, but the thing is, the ship's probably really heavy. Okay, so my guess is, just looking at it, it looks. I don't know. Actually, now that I look at it, the rotor's kind of too small.
Yeah. I mean, you have to have a rotor bigger than an Apache helicopter.
Yeah.
To kind of carry an Apache helicopter.
Yeah, now, that's more like a turbofan engine.
Yeah. There's like there's a scene where they do some combat in there.
Yeah. No. Now that I look at that image, yeah, you're right. That actually looks pretty off. That would have to be something like a turbofan, and I can tell you, like a turbofan of that size, like if you have 4 giant turbofan, engines attached to the side of an aircraft carrier trying to lift it. I don't think it's gonna fit. It's like
the engine that you make.
Yeah.
Even though it's an engine, can I think of it as a rocket? Can I put it under something and think of it as a lifter?
Yeah.
I'd have to work on the balance and stuff. So how much can you lift with that engine then?
So with one of those engines, if you build like maximum, I would say with one engine, 1,000 pounds is so if I had really big one,
if I had 4 or 5 of those, configured correctly, I could probably lift
a few thousand pounds,
or a few $1,000-pound flying saucer, right? Go back to that, right? So that's you'd have to get the thrust, and think you have pretty fine control over that, right? Absolutely. So if I had to turn that up and down, that's pretty cool.
I mean, definitely, like you have the possibility of creating. So you can use for VTOL, right? I mean, you can definitely create like some pretty interesting and weird, flying machines, like a little crab-like contraption, that like takes off and lands. Now, the cool thing about this would be that it can actually, the amount of payload you could lift in a compact platform would be pretty high. The thing with rotors and all that is that they're big and all that. This would be pretty compact. The other thing is that when you're operating like, when you're operating close to the ground and stuff like that, these turbines generally, it's a huge pain to operate them. But
let's check this out. So we've got the real life Iron Man here flying.
Yep.
Those are, what kind of jet engines is he got there?
So he's got a bunch of hobby scale turbojet engines.
This is that I think in this video, this is an old $6 million man, James Bond style thing, just to kind of show you what the history has been with that. But this stuff's a little bit more modern here.
Yeah, definitely. So he's got a bunch of turbojet engines. Basically, they're probably adapted hobby scale engines. In fact, one of them definitely is. So you can do that, but here's the thing, right?
That's really expensive, right?
It's expensive, but here's the problem I understand. So I remember once I had a chat with one of the jetpack companies, and what they described to me, the main issue that they had, the main challenge, with these things is endurance. It's like, how long can you stay in the air for? That is the real problem. It's the amount.
This one was 5 to 10 minutes.
Yeah. And for practical applications, the question, that everybody asks is, what can you do in 5 to 10 minutes? I'm I'm sure there's stuff. You see what I'm trying to say? I'm sure there's stuff, but I'm just trying to say that is the limitation that they're working with right now. It is really cool though. That stuff is really neat. I mean,
the Brits did some publicity ship to ship transfer. Yep. Can you take out a ship, going like this? It's borderline science fiction at this point, right? But I mean, anything new is borderline science fiction these days. Yeah. That's awesome. So what's next for Wave Engine? What can we expect to hear about on your website maybe in 2022?
Right. Yeah. So what what's new? So what we're hoping to actually get out in the next 12 months or so is the first. Right now, what you're seeing is videos and pictures of the first manned aircraft. Okay, and it's doing a certain amount of stuff. And what we want to do now, the next step of this is one, bigger engines. Okay, so more power, more thrust. Something that's
more noise.
Yeah. For initially, yeah. And then the second thing is that vehicles. Okay, so the first, what you saw just now was an adapted existing vehicle that was basically adapted for our engine, and it was just kind of like bolted onto the top of it. What we hope to have next is the first, custom built vehicle for our engine that is actually doing some really interesting stuff, faster.
So you're talking about building an airplane that uses this engine, not taking a glider and bolting it on.
A plane built for this engine.
Yep.
So basically, it's what we've been doing so far is effectively, taking a plane that was built for no engine or another engine and bolting our engine on, right? And that's not a great way to use an engine. For example, if I put a jet engine on a Cessna, sure, I could probably get it airborne, but it's not going to perform very well, Or if I did the reverse, I took a piston engine and put it on a, 747, not on a 747, but like on a business jet, it's not going to perform very well. The plane has to be built for the engine. And so for the first time, what we've gotten ourselves on a track for, with the government's help, is to build a plane for the engine. And I think that's going to be very exciting. And that's really going to start to show the world, what we can do with this technology, really start unlocking its potential. And that's, for 2022, stay tuned for that.
That's phenomenal. Well, I really appreciate you coming on the show today. A little bit more fiction and airplanes than cyber, but we got a little bit of that in there. And I think I've told you to lock your stuff down. I mean, this is you're a target, right? Industrial espionage. It's this is good
these days
stuff.
You can't be too safe. Yeah,
can't be too safe. So I'm glad we can help out with that a little bit. But where can people find you to learn more about this? Perhaps connect with you. Where can they go to learn more?
Yeah, our website wave-engine.com. All the info's over there, and feel free to reach out.
Awesome. Well, hey, thank you very much for coming on the show.
Absolutely.
This is Ron Gula signing off for another episode of Gula Tech Cyber Fiction, or in today's episode, Gula Tech Cyber Aviation, Fiction and Reality. Thanks again.